Good morning, good evening, good afternoon, wherever you are in the world. Thank you for this opportunity to present at ISQED 2022. We'll talk about 2.5D 3D heterogeneous integration challenges. Would like to acknowledge some of my co-authors and they helped me with the slides. Wilfred, Farana, Rob, Paul, and Noel Menezes for inviting me to ISPD. Legal information from Intel, a legal disclaimer. Thank you. Outline of this talk is going to be, we will introduce the problem, why do we do this integration and why do we pay that extra cost of assembly and bringing everything together. Then we will go through deep dives on two recent products, FPG and Lakefield. Then we'll talk about advantages and challenges that are remaining. And then we'll talk about the future. Where are we going with heterogeneous integration and also 2.5D 3D attachment methodologies or methods. In Before we start, let me just make sure that people understand what we talk about when we talk about 2.5D or 3D. Uh, if there is a base die and top die is attached to it, and the base die is completely overlapping the top dies, then it is Foveros or 3D stacking. Then the yellow embedded multi-die interconnect bridge that is shown here is the connection. It's a buried upside down die inside the package, which is as thick as a package metal layer. And then it connects the two dies, that is Intel's embedded multi-die interconnect bridge. Then there are C4 bumps, there are silicon interface bumps with SIBs, and a package will have traces. So the black traces are shown in the package. Another thing to note is that top die can attach using EMIB without a base die. Interposers can be silicon, organic, or glass. Sometimes optionally there will be a point, which is patch on interposer is also stacked between the base die and organic package substrate. And there are other alternatives like high density packages, hybrid metal bond techniques, etc. So just wanted to make sure that we understand the terminologies of what we are going to talk about in this presentation. Uh, Back in 1965, Gordon Moore, who was one of the Intel's founders, said that it may prove to be more economical to build large systems out of smaller functions, which are separately packaged and interconnected. He then said that we will be able to build such component crammed equipment. We ask under what circumstances we should do it. Essentially, the point I'm making is that in 1965, he predicted chiplets. Chiplets were going to happen. Finally, they are happening. And look at the vision of this person. Just wanted to make a point that chiplets have been proposed for a long time. Revisiting the past, 3D stacking is not new. I mean, 3D stacking exists since proposals exist for since 1980s, and first demonstration of TSP based 3D stacking are in 1990s. So it's not unusual. So we also worked on 3D stacking and published some of this work. We worked on a processor with a 3D stacked SRAM. SRAM was sandwiched between the processor and the package. We worked on voltage regulator where the 3D regulator was sandwiched between a processor and a package. We also presented some data on CPU DRAM stacking. That time, the challenges were manufacturing, assembly, and testing. Um, EDA, of course, the design tools were always challenging for 3D. And then power delivery, hotspot removal, hotspots misalignment, meaning hotspots tend to align. We want to misalign them, and thermals. And what happened during those times, like this is in the 2000s, continued technology scaling always overcame the benefits of 3D. If 3D was reducing the form factor, within two years, the technology will catch up and 3D benefit will go away. Now, what is the motivation for 2.5D or 3D integration? If we plot performance cost as a function of transistor design target or leakage power, we will see that no single transistor node is optimal across all points. If we also look at the functions, which is on the right side, logic or memory function, IO function, RF function, or mixed signal function, and if we draw a pentachart of where they belong and what are their requirements, they are not aligning. Everything has different requirements in terms of density, leakage, high voltage requirement, passives requirement, speed requirement. That means each of these functions wants its own technology. That means we have to do function dependent process selection. Another challenge comes from memory. AI workloads are exploding. I mean, they are just going high and high in network sizes, and it's very hard to accommodate full networks with data inputs and outputs inside a package and do the high performance computing. If we look at bytes per flop ratio from 2013, right from AlexNet to where we are going, it's a bit dated graph, but still in 2020, AI compute required 400 tops and it required 25 terabytes per second bandwidth of memory to compute. HBM tried to solve this. So HBM2E was proposed, and then we are presenting estimated power as a function of HBM bandwidth. And then HBM3 also tried to satisfy this 25 terabytes per second requirement. But if you look at the power is very high. There's a 10x power efficiency gap in this solution, HBM solution. Something has to be done. Power and memory, performance and memory bandwidth requirement is getting higher, and the energy efficiency gap is getting bigger. So we started looking into 2.5D 3D integration. If we plot interconnect density versus energy efficiency, there is standard packaging, embedded multi-die bridge, EMIB, Foveros, which is 3D, and future high density interconnect. We are going towards from only like 100 bump density per millimeter square to we are going to 10,000 per millimeter square with a very low energy per bit, 0.05 picojoules per bit. Today we are at about zero point 0.3, zero point 0.2 kind of picojoules per bit in 3D stacking, and in 2.5D we are about zero point 0.5. So we have to accommodate a lot of bumps and also make sure that we are under the power envelope that is supported by the power delivery and the thermal solutions. Intel has products in this space. For heterogeneous integration, FPGAs were the first. Two IR Labs Terafy chips, optical I/O chiplets, were connected over EMIB to Intel's FPGA, and this was published in 2020 and 2019. Lakefield was another processor that was done for mobile applications in Foveros technology, which had a 1274 or 10 nanometer compute on top of a base die, and then there was a package on package memory for a extreme form factor reduction. We will go through details of these two uh, products that are already out, and then two new recent products that were presented at ISSCC 2022 very recently in February. Both are for scalability. One is for Xeon side, Sapphire Rapids, which is high density Xeon solution with HBM, and then Ponte Vecchio, which is with HBM, but for graphics and high performance computing. Both of these have a lot of chiplets that come together in a heterogeneous fashion, and we manage all the chiplets to integrate them for a really high scalable solution with lot of compute and memory in the same package. Let's talk about FPGAs. So if we look at FPGAs, we will see that Intel Altera FPGA technology scaling, how we are progressing from higher whatever nanometers to 10 nanometers. It started becoming obvious that family of FPGAs would like to remain on the same node, while transceivers and chiplets can be updated, reducing the platform cost. FPGAs have programmable digital logic with configurable interconnect, and we wanted to talk a language to all these new chiplets that are coming in. So we will talk about the standard in a future slide. FPGAs are most sensitive to device scaling. They have speed, density, memory, bandwidth, all of those limit the performance of FPGAs. So it is ideal to go integration for yield optimization in FPGAs. What we did was we had a large FPGA die, 560 millimeter square, connected over EMIB to different transceivers. Once we do that, there are many advantages. The 14 nanometer 1 gigahertz FPGA in the first generation with 2.5D, and we connected it to 20 nanometer transceivers. And then transceiver roadmap was completely independent of FPGA roadmap, and both teams or both designs can progress towards providing better and better solutions as we go forward. All of this does not happen easily. We have to have a common protocol to talk between two different chiplets that are on two different technologies. So Intel made in advanced interface bus as an open standard. The specification is listed here. It is available on GitHub under Chips Alliance. We have AIB 1.1.0 standard and AIB 2.0 standard. We are going to 6.4 gigabits per second for AIB 2.0 with backward compatibility. Bump density is becoming very dense, meaning 36 micron pitch. Bandwidth per millimeter is going to be 1638 per millimeter. IO voltage is going down, which helps in power as well as energy per bit. And we are targeting energy per bit of 0.5 picojoules per bit in AIB 2.0. These are products that are announced and products are already happening. So these are real products and not just research solutions. Then let's talk about Lakefield, which was Intel's mobile alternative for mobile parts. It was a small form factor solution for making everything smaller. So SoC goals were to enable new class of compute devices in mobility form factor and compute at the lowest thermal budget and standby power. Standby power was the key. So we had to target 1/10 of the standby power of usual. At the same time, 50% graphics in performance improvement, 40% core board area reduction, and 40% height reduction for a small form factor. All of this could be achieved only with hybrid architecture with 3D IC integration, and that's what we call as Foveros technology. The top die had IA cores, high performance as well as low power IA cores, Intel architecture. We had graphics, media display, infrastructure processing unit, etc. DDR link, and the bottom die had lots of IOs. Bottom die connected to top die over 3D stacking, face-to-face bonding. Then we had micro bumps in the middle, and then we had package side bumps on the bottom of the base die that connected to a package to a BGA array, and we had the complete solution. We also brought in a 10 nanometer solution with P1222, which is like 22 or sometimes called 14 nanometer generation, now named Intel 16. Two different technologies together in 3D stack. And what we achieved on the left side, we could show that TSV did not really have any performance loss. And if we look at the Lakefield solution with respect to the Y skew in the mobile products, if we look at LP memory of LP3, LP4 versus LP4 in Lakefield, the core went down by 0.4x in size. Package became only 12 by 12, which was very small compared to the other packages. If you look at the dimensions, everything is half, so it's like a 1/4 size solution. We had POP, package on package memory, and we used PMIX to do the power delivery solution. Lakefield was deployed and used in various external products. So everything looks really good, and advantages of 2.5D 3D integration. I don't have to repeat what people have said already. It has lower portfolio costs, it lowers product costs, it lowers project costs. We can scale innovation and delivery capabilities because we can go faster in SKUs. We can make one product and make it alternatives of the same product very fast. So it's a granular leverage of die and process locked IP from internal and external sources. We can have granular leverage of manufacturing capabilities and capacity. We can mix and match process technologies, foundries, OSATs, assembly, test, everything together to bring together in a solution. And of course, there is a XY area reduction, memory comes closer to the logic, so we get better performance. All of this reduces the time to solution. We can reuse and reduce process availability, maturity, and IP porting. We can reduce the schedule and ramp risks. And because of the EMIB kind of solutions and also base die if they are passive, we can have 4x scalability over today, meaning 4 times a silicon die in a package that we have ever built. That means hundreds of distributed engines and gigabytes of memory inside the package. We really don't have to go to DRAM for many applications in hand or workloads that we are trying to solve with this 3D stacked processors. Doesn't come for free. There are challenges. Power delivery and thermals in a high performance, cost effective, high volume solution. Remember, it's high performance, cost effective, and high volume. All of them are coming together, then power delivery and thermals remain as bigger challenges, something for ISPD audience to understand and also work on. There is a tiling tax. So there will be an incremental area power performance paid for die-to-die interfaces. There is a package assembly test cost and duration cost for making all this happen. There will be tolerance requirements. There will be throughput time requirements. There will be inventory management problems. Uh, we also saw that you cannot co-package multiple hot die in the with together. So you have to manage the thermal solutions as well as like performing dies should go together if you have variability in your products. There is also margin stacking and inventory carrying costs that we have to manage. There is another statement I'm making here is that this is not always optimal in the cases where monolithic alternative is feasible. This is a loaded statement. Feasible is the correct word, meaning if it is feasible to make a monolithic die, we will make a monolithic solution, but it doesn't seem so. These days, various functions have to come together on different process technologies, and hence we cannot be monolithic. Uh, Die designed for 3D stack is difficult to use for 2.5D, for example. We need to enable IPs, IP repository, software repository, tools, flows, and methods. And the interface standards and interoperability has to be fully specified. That's the next slide. I wanted to make a point that interface has to be standardized at mechanical, thermal, electrical, and functional level. Each of these avenues have different requirements and we have to satisfy a standard. We have to support generational compatibility as we go forward and provide different generations. All can be enabled by off-the-shelf tools, flows, and methods and hardware software building blocks. And once that happens, then we can support an industry scale systematic reuse and and many companies can come together to form alliances and provide better and better products as we go forward. I also want to make sure that we understand that software is a big challenge. We went from board level integration to package level integration and on-die integration. In all these cases, the software has to be uniform. Software should not see a difference in what kind of integration you are using. Ideally, IP and associated application software should be agnostic to scaling and physical integration. And once that happens, it enables right sizing functionality for a wide variety of target deployment environments with high reuse of IP, system, and software investments. Uh, Finally, let's talk about where are we going. So in terms of future of heterogeneous integration, Intel has published gallium nitride based wafer to wafer bonding as well as monolithic 3D solutions. So we are proposing to use gallium nitride highly densely integrated for power delivery and RF applications. That solves the, the high voltage device problem. Then compute can stay as is, and then we can also integrate different memories. So we have presented alternative memories that we can manufacture: RAM, STT-MRAM, anti-ferroelectric EDRAM. All of those were published, and the graphs are showing that they are working, they are functional, and they can be integrated if required by a product to give better value of a product. This is where we are going. We are bringing heterogeneous devices and memories and sometimes heterogeneous interconnect like photonics in a system, so to give a better energy efficient solution or a high performance solution depending on the customer's needs. Final slide. So where are we going with now? That was heterogeneous integration. Where are we going with 2.5D and 3D? 2.5D and 3D attachment is mainstream. Innovations are continuing. Lot of innovations are happening in various domains. Many old challenges are mitigated, and hence we can offer many products that are energy efficient as well as cost efficient. It is reducing overall product cost with higher energy efficiency, as also seen by some of our competitors and industry partners, that smaller dies are yielding better. So you can have larger solutions of smaller dies instead of big dies coming together in a package. And in terms of attachment technologies, we are going towards Foveros Omni, where Top dies can connect directly to package and not go through base die, so we can have high-speed I/O solutions. And Foveros Direct, which is copper to copper bonding with no bumps, direct bonding, that means less capacitance to worry about and smaller drivers, less power, and better, wider, low power die-to-die interface connection. With that, I would like to conclude and thank you very much for listening.